Darling, you got to let me know. Should I stay or should I go? If you say that you are mine, I'll be there till the end of time. So come on and let me know. Should I stay or should I go? Hello everybody, welcome to this week's edition of Video Notes for Mr. Flugum's AP Chemistry class. Today we'll be talking about enthalpy, which continues our discussion of thermodynamics. So what enthalpy is about measuring the amount of heat that is released or absorbed in a chemical reaction. Let's go ahead and get started here. Alright, so basically enthalpy is this, right? It's represented by this symbol right here, delta H. Okay, that is enthalpy. And as I said in the intro, right, it is the heat released or absorbed in a chemical reaction. So here's the deal, right? This is the heat that's released, right? And we can measure that by taking the heat contained within the products and subtracting from that the heat that is contained within the reactants. All right. So, and we'll explore this idea as we go through, but this is the basic concept, right? Is the difference in heat. So here's the first idea with enthalpy, right? It's this. It's when you have a chemical reaction, when you reverse that chemical reaction, the same amount of energy is basically taken in or put out. So for example here, when we have the synthesis of water, which may happen in, say, a hydrogen fuel cell, okay, you have a delta H of negative 572 kilojoules. Now when we take that same reaction and run it backwards, the other direction, decompose water into hydrogen and oxygen gas, it is a delta H of positive 572 kilojoules. So basically, when we reverse a reaction, right, the same amount of energy is required. It's just which direction is that energy moving. So how can we find this delta H, this enthalpy? Well, there's 4 different methods. They're listed here. Today we are just, in these video notes, we are just going to look at this idea right here, to calculate it using average bond enthalpies. At other times we will do things such as using a calorimeter or Hess's law or using enthalpies of formation. That'll be for later down the road. Okay, I want you to think back to when we talked about bond energy and potential energy, right? And remember, as atoms move closer together, right, their potential energy decreases, which means that energy has to be changed into something else. Normally that's heat, but it could be a lot of other forms of energy. So when we form a bond, energy is released, right, because the atoms are becoming closer together. In the vice versa, right, on the flip side of the coin, right, the same amount of energy has to be added in order to break that specific bond. Okay, because remember, potential energy increases as atoms move away from each other. That means we've got to put energy in, okay, take energy away from the surroundings in order for that bond to be broken. Okay, so let's think about this in theory, all right? If we are to find our change in enthalpy, we need to find the sum of the bond energy of the bonds that are broken and take away from that the bond energy of the bonds that are formed. So in other words, we've got to do this, right? This is the bonds of the reactants. This is the bond of the products. So think about this in theory. We have this reaction over here, right? Where we have element A that forms a diatomic atom, a molecule, excuse me, and it combines with B. Now, in order for this reaction to happen, we have to break that bond between the A atoms, which takes about this much potential energy right here. Okay, so once those are broken apart, now we can combine. Now, if those atoms were going to go back together, it would take exactly the same amount of energy. But they aren't. A is now going to combine with B, which takes a different amount of energy, which you can see here. in this case, that energy is released as those two atoms come together and form their new bond. Okay, and that means this, right? That the reactants and the products end up with a different amount of potential energy. All right, folks, so let's talk about how we can make predictions based on enthalpy about whether something will be endo or exothermic. So let's take our first example here, and you can see on these graphs we have potential energy on the y-axis and the reaction time on the bottom, right? In this case here, we start with our reactants and end with our products. Now in an endothermic reaction, you can see that the products have a much higher potential energy than the reactants. Well, that means this, right? That energy was taken in and stored in those bonds, right? Which means we have a much higher potential energy. Okay, so that means this, that our enthalpy in the case of an endothermic reaction is positive because we are adding potential energy or adding energy to the products. Exothermic is different, right? If we start with our reactants here and end with our products, we end up with a lower potential energy. That means our enthalpy, our delta H, will be negative because that energy is being released from the reaction and given off into the surroundings. Okay, folks, so let's use a practical example here to find our delta H, our enthalpy of this reaction right here. So remember, to do this, we need to take the sum of our bond enthalpy of our reactants, and we also need to find the sum of our bond enthalpy of our products. And then we need to subtract those from one another, right? Reactants minus products. So let's go ahead and do that. Okay, so here I have our calculations. Here is for the methane right here, and we're using these bonds right here, CH. If you notice, there's 4 carbon-hydrogen bonds in a methane molecule. So we gotta multiply those together. And then we also have 2 oxygen molecules, right? 2 oxygen molecules, so we gotta say, okay, that forms a double bond. 2 times 495 gives us 990. If we add that all up, the sum of our reactant bond enthalpies is 2,642 kilojoules per mole. Cool. Now we got to do the same thing with our products. So here I'd put our calculations for the products on here. We have 2 carbon-oxygen double bonds. Think back to when we did Lewis structures, right? What would that CO2 molecule look like? Well, it has 2 double bonds between the carbon and the 2 oxygen molecules. It gives us 1,598 kilojoules. And we have 2 water molecules, and each water molecule is going to have 2 bonds, 2 oxygen-hydrogen bonds. Therefore, altogether, we've got 4 of those bonds. So we multiply that out, we get 868, which gives us a total of 3,466 kilojoules per mole for our products. Now we just need to subtract, right? 2,642 take away 3,466, and that gives us a total of negative 824 kilojoules per mole. Now if you notice here, our answer is negative. That means this is going to be an exothermic reaction, right? Heat is given off because there is more heat absorbed, okay, there is more heat given off than there is absorbed as the bonds are broken and formed again. And of course, we know this is a combustion reaction, right? It should be exothermic, huh? Could have predicted that ahead of time, I guess. Well, thanks for tuning in, folks. I've got another example for you, but I wanted to save that until we get to class on Friday. Then if you have questions about how we do the calculations for this and things like that, we can answer them then. Hope you have a great day. We'll see you in class.